This is 2009 AP Physics B FRQ question, and look it up. I will post the link in the video, and look up the question, try to solve it first, and then go over the explanation if you're still confused or you could not solve something. So the problem states, a metal rod of mass 0.22 kilogram lies across two parallel conducting rails that are a distance of 0.52 meters. So the distance between the rails is 0.52 meters, and that's on the graph, and then they show the rod on a tabletop as shown on the top of view above. 3 ohm resistor is connected across the left end of the rails. The rod and rails have negligible resistance but significant friction, with a coefficient of friction of 0.2. There is magnetic field 0.8 Tesla perpendicular to the plane of the table. And it is into the page, not out of the page, because we see those crosses. A string pulls the metal rod to the right with a constant speed of 1.8 meters per second. Let's look at the question. Calculate the magnitude of the current induced. So we need to calculate the induced current in the loop formed by the rod, the rail, and the resistor. So to calculate the current, I need the induced EMF divided by the resistance. The induced EMF is equal to the change of the flux over the time. And the flux has the formula of B, magnetic field, through the area, cosine theta. And theta is the angle with the normal to the surface through which magnetic field is passing over the time. Then I have, because our angle is perpendicular, so it's 90 degree, it's 0 degrees with the normal, so the magnetic field is perpendicular to this surface, and so is the normal perpendicular to the surface. So the normal to this surface where the magnetic field is passing through and the magnetic field are parallel to each other. So that means there is 0 degrees angle, and cosine of 0 degrees angle gives you 1. So I don't have to write this one. And the area through which the magnetic field is coming through. So I have B, and then the area is the length and the width. So that is the length, the width, cosine of 1, and over the time. L over T, so if this is your L, and if it's over T, that is going to be the velocity at which the rod is moving. So your current is equal to, so I could write this is equal to B, V, and the W, the width. So now if I plug in the numbers, I have I is equal to the magnetic field is 0.8, the velocity is 1.8, and the width is 0.52. That's how far the rails are apart from each other. Oh, and I don't have to write the time anymore, so the time is already gone with L over T, giving me velocity. And this number is equal to, oh, and I also have the resistance, right? So I'm going to use this formula over the resistance, and the resistance is 3 ohm, and that gives me 0.25 amps. So for B part, I need to calculate the magnitude of the force required to pull the rod to the right with a constant speed. If I look at my question here, this is the force that is applied, and I'm going to call this the tension force. At the same time, there is the friction force, and I'm just going to add them together, so there's 2 of those. So there is some friction. And then I don't have to say 2 frictions, I don't want to confuse you, but this one there is 1 friction for both of them together. So there is going to be the friction force this way, added together from those 2. And there is going to be the magnetic field force, because the whenever you change the area through which magnetic field is coming, the closed area, it always opposes the change. So the magnetic field, so if you expand the area, like in our case, then magnetic field is going to be acting on the rod in the opposite direction of what you're doing. If you moving the rod to make the area smaller, then the magnetic field is going to be opposing. So magnetic field does not like the change, or the change of the magnetic field will always be opposed by the current that is present there, and that will cause the force, the magnetic field force. So I have to find 2 forces, and that is going to be the tension force. And they ask you to find in B the magnitude of the tension force to cause constant speed. So if I say my tension force is positive for the net force, and friction and magnetic fields are negative, then the acceleration is equal to 0. So for the B part, I have the tension minus the friction force and minus the magnetic field force is equal to ma, but acceleration is equal to 0. So I have a 0. So the tension must be equal to the friction force plus the magnetic field force. So the tension is equal to mu, and because it is sliding, so it is kinetic, mg of the rod plus the magnetic field depends on the magnetic field force depends on the magnetic field, on the current through that rod, and how much of that rod is in the magnetic field. So if I plug in my numbers, I have mu is 0.2. The mass of the rod is 0.22 times 10 gives me 2.2, plus the magnetic field is 0.8. The current I just found 0.25, and the length of the rod is the distance that they are apart, 0.52. So that's the area, that's the length through which current is coming through and affected by the magnetic field. So if I plug in all my numbers, it's not I, it's tension, I'm gonna get 0.54 newtons. So that's the force at which you have to pull the rod in order to cause that EMF that causes that specific current, or causes to move the rod at a constant velocity. For C part, they ask you calculate the energy dissipated in the resistor in 2 seconds. So here's more information given in 2 seconds. So the energy dissipated by the resistor is the work done, and the work done is equal to the power times the time. So the work is equal to power times the time. And the power because the power has formula how much work over time. So if they say how much energy, so they say calculate the energy, so that I have to calculate the work done by the current moving through. So the power is IV times the time. And because I have resistance and I have the current, I can use a different formula. So instead of IV, I can say I squared R times the time, because V is equal to I times R. If you have I times V, that gives you I squared R. So the work is equal to I is 0.25 squared. The resistance is 3, and the time is 2 seconds, and that will give me 0.375 joules. So that's how much work will be done by the current flowing through the resistor. For D part, they ask you to calculate the work done by the string pulling the rod. So the work done by the string pulling the rod is equal to the tension force times the distance that it got pulled, and over 2 seconds. So here is more information here, and that gives me the tension force is 0.54, and the distance is average velocity, which is 1.8 times the time, and that gives me the answer of 1.944 joules. So that's how much work needs to be done in order to pull the rod for 2 seconds this distance. And here's the last part. Compare your answers in part C and part D. Prove physical explanation for why they are equal or not equal. And we see that they are not unequal, right? They are unequal. They are unequal because the work done by the tension minus the work done by the friction is equal to the work done by the circuits. So I have my work done by the tension 1.944 minus the work done by the friction. So it's the force of the friction, mu, the kinetic friction, and then mg, and the distance, which is the velocity times the time. I'm going to plug in the numbers in a second. So times the time. So it's the force of friction times the time. And that should be equal to the work done by the resistor, the rest of the energy, which is 0.375. So if I plug in my numbers, I have 1.944 minus the mu is 0.2. The mass times g is 2.2. The velocity is 1.8. Time is 2 seconds. And that should give me 0.375. And let's see if it's true. Yes, and that gives me 0.36 is equal to 0.375. Probably because of our rounding, the answers were not exact, but almost the same. So not all the work that is done by the person or the machine that is pulling the rod is converted into the heat and energy that the resistor takes away. So some of it is taken away by the friction.